Good afternoon, everyone. I'm going to be talking about an area just to the east of Copernicus, which you just heard in this previous talk. So the area that I'm interested in has the Sinus, Aestuum, Rima, Bode, and Mare, Vaporum. So early on in studies of the moon, you could see these highland areas that were very dark as the Mare. And so these were called dark mantle deposits. So you can see that they're so they were low in albedo, they're smooth surface, they mantle the highland terrain. And then as remote sensing data was collected, they were determined to have iron and titanium. So they were interpreted as volcanic glasses, otherwise known as pyroclastics, that were produced in explosive volcanic eruptions. So once Apollo 17 and the other Apollo landing sites, but in particular at Taurus Littrow, the astronauts identified like this orange patch here. And when they brought it back to the laboratories, we found that it was made up of these volcanic orange glasses or crystallized dark black beads. So whether you got the glasses versus the beads, the crystallized beads depended upon your cooling rate. So if you quenched, you formed the glass, and if you cooled slow enough in these gas-rich plumes, you could form olivine and ilmenite. So depending upon the ratio of glasses to crystallized beads, you can learn something about the optical density of the volcanic plume. Okay, thank you. So because these glasses were produced in these volatile, rich, explosive eruptions, we learn a lot about the interior. So again, thanks to these Apollo samples, we learned that carbon monoxide and water were the dominant gas species that drove these explosive eruptions. And so over here, you can see a model of what we think happened. At say 500 kilometers or more depth, we had this melt, which then as a dike propagated to the surface, it built up this kind of magmatic foam rich in gases that then erupted on the surface, producing the pyroclastics. So the M-cube data showed that from work by Millikan and Lee and Millikan, that these regional pyroclastics were rich in water. So the area that I'm looking at is shown by this yellow rectangle. So here is Rima Bode. You can see it has high up to 400 parts per million water. Mare Vaporum is more moderate. And then Sinus Aestuum actually is the only regional one that does not have a signature of water. But interesting enough, if you look at the M-cube data, you can see that Sinus Aestuum actually has this spinel, which we think is iron rich. So clearly the Sinus Aestuum represents a distinct kind of eruption compared to these other regional deposits. So what we've been doing is producing a USGS map at 1 to 1 million scale. So we've used various data sets to try and map all these units, and we divide them up into 23 geologic units. And one of those units is the dark mantle deposits. So the main difference between our map and some of these older maps is that we've mapped a lot more of the smaller Mare units. We have identified more faults and surface features. We've been mapping some of the crater units for the larger craters. And of course, for the dark mantle deposits, which we were most interested in, we've actually divided them up into 3 distinct units. So as an example, here is the WAC mosaic, so showing Rima Bode and a portion of Sinus Aestuum. So the early maps like Wilhelm's 1970, you can see this ID unit shown in orange. That corresponds to where the dark mantle deposit is actually the darkest. But if you look at some of these other data sets, the newer ones, you can see, for example, the TiO2, that the dark mantle deposit extends much further out than was previously mapped. In Sinus Aestuum, we can see the spinels this far out as well. So what we did is we divided the dark mantle into 3 units where it's either darkest, where it has kind of a thinner and more moderate albedo, And then where it's diffuse, you wouldn't be able to tell from albedo that there was a dark mantle deposits, but the other data sets show us that the glasses, and in the case of Sinus Aestuum, the spinels extend that far. So unfortunately, these regional deposits have all been covered up partially by the younger Mare, but there is an example on the moon of a larger regional deposit where we can see its full extent, and that is this Orientale dark mantle deposit. And so this has been modeled as this gas-rich magnetic foam that penetrates through a dike, comes to the surface. You erupt into a vacuum and produce this nice umbrella style plume. And so you get this very circular ring of dark mantle deposit. And then eventually, once you've erupted everything, the vent forms during the collapse. So here is the vent. So what we can do is then make a guess of what that original dark mantle deposit would have looked like if we just fit a circle to where it's darkest, as was done at Orientale. So these inner smaller circles represent where that umbrella kind of style plume would have occurred. And these stars represent where the center, the vent would have been located. And you can see it's always in the Mare and would have been buried. The larger circles represent, though, the furthest extent to where we see the pyroclastics. And so you can see that they actually cover a very broad area. They extend, in case of Vaporum, all the way out to where the vent would have been. So that's very different from this annular ring that formed the Orientale. So we know it was a different kind of eruption. It wasn't all gas rich like it was at Orientale. So instead, it's more likely that these eruptions formed in these Hawaiian style eruptions where you could have originally started with a very gas rich plume, which then it allowed the pyroclastics to extend out to the furthest distances. And then eventually, as you depleted some of the gas, you transitioned to this more Hawaiian style where you're erupting magma as well. And so then you might have concentrated more of the pyroclastics closer into the vent. And so you can see sort of these range of ejection velocities that you would have gotten. And it must have been quite high in order to get to the furthest distance at Sinus Aestuum, which is 220 kilometers. So in terms of future exploration, these are quite interesting and I think would be very valuable if we could do sample return or even human exploration. As I said, we have Apollo samples already, the green glasses at 15, the orange glasses at the 17 sites. So it'll be interesting to compare some more pyroclastics to those already collected. We can assess the eruptive styles, that in particular looking at the ratio of glasses to crystallized beads, what kind of compositions are present, and what is the relationship to the associated mares that we think erupted with the pyroclastics. We can learn more about the role of water and other volatiles in the eruptions. The dark mantle deposits are very interesting for in situ resource utilization and future human exploration because they are rich in iron and titanium, so that could be used for building. And obviously because of the volatiles, those could be used for water for astronauts. The DMDs are on the highlands. So in this particular area, we're on these Imbrium highlands. And so we could learn more about the formation of these massifs and the highlands themselves. And then as you heard, the Copernicus is just to the west. And so if we could sample some of the ejecta from Copernicus and Eratosthenes, then that would help us nail down the geologic time scale for the moon. So to compare the three sites, there's lots of pros and cons for each. In particular, Sinus Aestuum, you've got a large area, but you don't have the water signatures. But you do have the spinels. At Rima Bode, you have the highest water contents, but no spinels. And at Vaporum, it's more moderate water contents and no spinels. It's also rugged at Vaporum. So to summarize, we've done mapping that shows that the pyroclastics extend much further than had previously been mapped. That indicates larger eruptions. It's unlikely that these were gas-rich plumes like at Orientale. Instead, these were more likely Hawaiian-style eruptions. All three of these would be very compelling for future exploration, both for volatiles and for in situ resource utilization. I think the Sinus Aestuum would be great if you really wanted to look for spinels, but you wouldn't get the water. If you went to Rima Bode, that of course would have the water, and you're going to hear more in a talk tomorrow by Sasha about details about Rima Bode exploration there. And so perhaps the best spot would be in that red triangle where you have overlap of the pyroclastics from both Rima Bode and Sinus Aestuum. So you would be able to get hopefully samples from both of those. Thank you.